Our lesson for today will be looking at Chemistry 1502. The topic for today is Geometrical Isomers. We will be looking at Cis-Trans Isomerism, lesson 101. Let us start. First of all, let us look at the definition of geometrical isomerism. When we talk about geometrical isomerism, we are talking about the different geometrical arrangement of the groups or atom about the double bonded carbon atom. Before we can explain this using organic chemistry terms, let us forget about chemistry now. Let us look at this general explanation. Suppose we have a piece of paper, and then we take another piece of paper, then somehow we take a nail, a very thin nail, we pierce the first paper right through to the second paper. And by the way, this is not a double arrow. Like I said, forget about organic chemistry. We are not talking about electrons here, we are talking about just a nail. And then we label this corner as A, B, C, D. If we try to rotate the second paper, let's say this is paper 1, paper 2. If we try to rotate the second paper, which is paper 2, we do agree that it will be possible for it to rotate freely without any problems. But let's say we take another nail, we pierce it right through the first paper. With the second nail into these papers, we do agree that it will be impossible for the rotation to occur. So there's no rotation. So if we understand this general explanation, then let us go to organic chemistry. Suppose we have alkane, this serves as that single nail, and then we have alkene, and then this will be our two nails. So we do agree that we have carbon number 1 and 2. Carbon number 2, it will be possible for it to rotate freely because of this single nail. Then looking at alkenes, it will be impossible for the rotation to take place because of these two nails. So you should understand that when you are dealing with a single nail, alkanes, whereby there is a rotation, we cannot talk about geometrical isomer. So if it happens, let's say we have multiple choice questions, and then they ask about geometrical isomerism, and then one of the options you are given an alkane, you should know that it is impossible for us to have geometrical isomerism in alkanes, whereby there is free rotation. But dealing with alkene, whereby there is no rotation, you should know that geometrical isomerism, it is possible. So in simple terms, when you talk about geometrical isomerism, we'll be focusing on alkenes. That is one of the conditions that we have to look at when we are talking about geometrical isomerism. Under geometrical isomerism, we have cis and trans. When the similar groups lie on the same side, it is called cis. The key word cis, just remember, same. What I normally do, just to make sure that you do not forget this, cis, and then let us put this S with capital letter, which stands for same. Now if we can remember that cis, same, that has S, it's same, simply means same side, then we definitely know that the other one will be opposite. And remember that we do not consider the word that has many alphabets compared to the other one. Let us just say the three-word term that has S will take say, and then the other one will take opposite. So we have cis, which is same side, and then we have trans, which is when we have similar groups which are on the opposite side. We call it trans. Write this down. We are going to use this. Now let's look at examples. Remember that we are dealing with alkenes. I normally say we should not say groups only but atoms. So it's groups or atom. We just identify where they are. Are they on the same side or opposite sides? In this case, we can see that we have hydrogen, and we have, so this one we have on the same side, so it's cis. Looking at the name for this IUPAC name, we have 1, 2, 3, 4. So you can see that the parent chain, it has 4 carbons. So we have boot. Let me actually use small letter. We have boot. Then since we have a double bond, we can say butene. And then where is the double bond? Even though we can count from the left, we are still going to have carbon on the second, the double bond on the second carbon. 1, 2, 3, 4. So the double bond is on the second carbon. So we can say boot 2 in. So that is the name. Now to show the stereo isomer, we include this in the IUPAC name. So it will be cis. Let me not actually diverge from the knowledge that we've gained. Remember we said there's hyphen between numbers and words. So let us put it like this. Instead of putting this the location of the double bond within the name, let us say 2 butene, such that when you combine this and this, we are going to put hyphen, then it's 2 butene. So it says 2 butene. Since we have cis butene, do we have trans isomer of butene or 2 butene? Yes, we can start by drawing our carbons with a double bond, and then instead of having hydrogen on both sides, let us put hydrogen here and here, and then we put the methyls here. Somehow it might sound like, or it might seem like this is the branches, but it's just a way we can show the cis-trans isomerism. So you can see that we have hydrogen on opposite sides, and methyl on opposite side. So instead of saying cis, we are going to say trans 2 butene. And if we want to represent this using a skeletal structure, you can clearly see from this structure. So we can draw it like this. Put a double bond here, and then we focus on carbons which has are involved in the double bond. So we have hydrogen here. We know that when we're dealing with skeletal structures, we don't show the hydrogens, but we have hydrogen here and hydrogen here. You can see that they are on opposite sides, and these are the methyls that we've shown here. So this will be trans using a skeletal structure. Looking at the cis, the skeletal structure will be like this. Put a double bond here. And then our hydrogens will actually be here. What you should know is that geometric isomers possesses the same structural formula containing a double bond and differ only in respect of the arrangement of atoms or groups about the double bond. So in general, we could say that geometrical isomerism is shown by alkenes or their derivatives, in which two different atoms or groups are attached to each carbon containing the double bond. So we do not expect alkanes to have geometric isomerism. Another important thing that you should know about cis and trans isomerism is that the trans isomers are more stable than the corresponding cis isomers. Should it happen that in the multiple choice questions this type of a question is asked, you should know that the trans are more stable than the cis isomers. This is because in cis isomer, the bulky groups are on the same side of the double bond. The static repulsion of the groups make the cis isomer least stable. Another thing which is very important, you should know that not all alkenes show geometric isomerism. It is only possible when each double bonded carbon atom is attached to two different atoms or groups. For example, let us look at propene. Looking at skeletal structure of propene, we have something like this, and then we have a double bond here. But let us use another way to represent this. We have the double bonds here, and then we have our methyl here. We have hydrogen here, we have hydrogen here, and we have hydrogen here. Looking at the skeletal structure, we know very well that we have hydrogen here and hydrogen here. And then this is just a methyl. So in this case, let us look at this. We cannot talk about cis-trans isomerism. The reason why, the second carbon, actually the first carbon, which is this one, you can see that it is bonded to two same or similar groups or atoms. So in this case, we cannot talk about isomerism. The second carbon, we can say somehow it satisfies the conditions to be a cis or trans, because you can see the first group is not the same as the second group. But for this one, as you can see that the groups are the same, we cannot talk about cis and trans. And yes, it is an alkene. This supports the statement to say not alkenes, not all alkenes, they can be cis and trans isomerism or isomers. Let's look at another example, 3-hexene. Try to pause the video, work this out, and play the video. And if we do have cis and trans isomers, write down or draw the structures of cis and trans isomers of 3-hexene. Hexene means 6 carbons. So let us start by drawing our double bond, and it should be on carbon number 3. The best way to start drawing this, let us do this. So we have 1, 2, 3, 4, 5, 6. Now I'm actually training you for examination. So we have carbon 1, 2, 3, then we put a double bond here. Then from there we can simply put our single bonds. And then from here We know very well that this carbon, it has bonded 3 times already, so we just need hydrogen. Then the second one, it is also bonded 3 times already, we need hydrogen. And then from there, let us try to bend this part to be this side and also this side, and see what actually happens. But instead of bending, let us just do this. We have CH2, CH. Let me do this using a condensed CH3. Do the very same here. Very same thing here. CH3. So looking at this, does it qualify to be a cis-trans isomers? Now you can see, looking at the first carbon, which is this one, it is bonded to 2 different groups, which is this one and this one, the ethyl and hydrogen. Looking at the second one, which is identical to the first one, you can see that it is bonded to 2 different groups. So yes, this qualifies to be a geometrical isomer. And then if we put it like this, it means that we have to bend this, and then it will be a cis 3-hexene. And then for the trans, we're just going to put everything. Like I said, we have to bend this so that it becomes this side. Remember, we need top and bottom. So this will be CH3, CH2. Then by the way, this will be at the, let me actually write this in a correct manner. Let's start with cis. Remember, cis means same side, so this will be cis. Then looking at trans, you're going to have one of the ethyls on top and at the bottom. Then we have hydrogen here, we have hydrogen here. So this will be trans 3-hexene. But don't look for up and down only. Let us look at a butene dioic acid. It's butene dioic acid, which the molecular formula is like this. You can clearly see similar groups. So we can decide to draw it like this. Put a double bond here, and then we put COOH here, then we put hydrogen here. This part is actually this part. This part is this part. And then we put COOH, which is this part, this side, and then we put hydrogen here. So the question is it a cis or trans? You can see that it's on different sides. This group, similar groups are on different sides. So this is trans, butene dioic acid. If you want to draw the cis isomer, you're going to have COOH, COOH, then hydrogens here. This will be cis, butene dioic acid. In the next lesson video, which is lesson 102 of Cis-Trans Isomers, we'll be looking at more examples, doing more examples for practice purposes. The next lesson, which will be the EZ system or nomenclature, you should also watch it. It's very important. It goes hand in hand with cis and trans isomers. But what is important is to watch this lesson before that one. This is Bahula SJ. Thank you very much.